Hi, I'm Allison Douglas, and I'm a product manager at Agilent Technologies. I've been supporting our one-box testers and channel emulators for 7 years, and I'm going to show you how they work together for a cost-effective solution for MIMO over-the-air test for LTE devices. Requirements for MIMO OTA are being largely driven by cellular operators who want to ensure that the field performance of their devices is satisfactory to their end users. 3GPP will be requiring MIMO OTA test as part of their LTE conformance standards. CTIA and 3GPP are currently discussing what those standards will be, and Agilent is actively participating in those discussions. The ultimate goal of MIMO OTA test is to be able to distinguish a good handset or device from a bad one. Agilent's engineers have come up with an innovative new method to help LTE antenna and device designers quickly and cost-effectively validate the MIMO over-the-air performance of their LTE devices. I will now walk you through Agilent's proposed solution for MIMO OTA test, the two-stage method. The two-stage method combines the benefits of traditional anechoic chamber radiated measurement with the flexibility of digital channel emulation. This fast, efficient, and cost-effective method provides a solution for engineers to perform design validation test until 3GPP and CTIA decide which test method or methods will be supported for MIMO OTA test. In stage 1 of the two-stage method, the device under test is placed in a standard far-field anechoic chamber and is stimulated by a signal from the PXT, Agilent's LTE base station emulator. The antenna gain is measured while the device under test is rotated inside the chamber. This gain information is used to generate a 2 or 3D antenna pattern that will be used in stage 2. A graphical representation of this antenna pattern can be seen here and here. The setup I have here is stage 2 of the two-stage method. Our PXT is generating a 2x2 downlink MIMO signal, which is being fed into 2 MXA signal analyzers where the signal is digitized and down-converted to baseband. The signal is then sent digitally to our PXB baseband generator and channel emulator. This is where the fading channel model and the antenna pattern gains are applied. The signal is then sent digitally to our 2 MXGs. This is now our faded downlink signal going to our device. Since the antenna gains have already been applied, we're accurately characterizing the over-the-air performance of our device through our cabled connection here. The uplink signal from our device is then going back to our PXT where we can measure the physical layer throughput. There are several LTE channel models specified for MIMO over-the-air test, which replicate real-world MIMO conditions and channels and generate realistic fading scenarios including path and channel correlations. The PXB emulates these channel models. In our demo, we will be using the SCME urban macro cell model. The PXB is also digitally applying the antenna gains from the antenna pattern generated in stage 1. The favored metric for determining if a MIMO device is good or not is throughput. With our existing call parameters set up on the PXT, the maximum throughput of this device is 19.82 megabits per second. We've lowered the cell power to a level where we are beginning to see some impact of the receiver sensitivity. As you can see, our throughput is slightly below the maximum rate. Now let's see what happens to our throughput rates when we start rotating the antenna pattern. The data rate we just measured was for 0 degrees. Now on the PXB, we can rotate the antenna pattern to simulate rotating your device inside an anechoic chamber. We will rotate the antenna pattern to 90 degrees and run the throughput test again. You can see an improvement in throughput, which is what we expect based on our antenna pattern that has a higher gain at 90 degrees. We can continue to step through rotation angles until we have a complete set of data for a given cell power level. This can be repeated for multiple power levels to get a more complete picture of the data throughput rates for different angles of rotation and cell power levels. This is what a typical set of results look like, with angle of rotation on the x-axis and throughput on the y-axis. If we then average the throughput values across the angles of rotation for an individual power level, we can chart cell power level versus throughput. This gives us the information we need to show the over-the-air performance of a MIMO LTE device and meet our initial goal of distinguishing a good device from a bad one. As you've seen in the demonstration, Agilent's flexible two-stage method using the PXT and PXB provides a cost-effective and efficient solution for validation of LTE devices. I hope you found today's demonstration useful. For more information on Agilent's MIMO OTA solutions, please go to the URL shown below. Thank you for your time.